Welcome to video clip 3.6, in which we map bpmn process models to Petri nets. First of all, I'd like to discuss the relationship between Petri nets and soundness. I was mentioning earlier that Petri nets are used as a formal vehicle to precisely specify a soundness property of process models, of Petri nets in particular. The idea is here to use a reachability graph to determine the soundness of a Petri net. However, we have modeled the Petri net with bpmn, so there is a gap in the notations used. So we have on the one hand side, we have the bpmn process models, which we like to analyze. On the other hand, our techniques and our formal notations use Petri nets. So there is a gap, and we, in this video clip, like to bridge this gap. So how we do this? The next steps, we provide a mapping from bpmn to Petri nets, from a subset of bpmn, a widely used subset, but not, let's say, the complete bpmn set. We check soundness properties 1, 2, and 3 that we learned already using the reachability graph of the corresponding Petri net. Can use the reachability graph we just took a look at to analyze soundness. Of course, we also need the concept of structural soundness. So a Petri net is structurally sound if it has one dedicated initial place that has no incoming arc. That's the initial place I. If it has one dedicated final place O that has no outgoing arc. And if each node in the net lies from I to O. So that's basically the same definition as that we borrowed actually for bpmn process models regarding structural soundness. And in this case, the Petri net is also called a workflow net. Workflow net is also used very often in the academic BPM community. So how can we translate bpmn process models to Petri nets? The idea is we take bpmn activities, events, and gateways and map these to Petri net subnets to using the structures, using places and transition we learned from Petri nets. In the example, we did that already. So we had the activities, and then we had the transitions for checking an order, something like that. These subnets are connected such that that they represent the behavior of the business process model. Intermediate events and tasks are mapped to transitions. And the bipartite structure of Petri nets also requires some additional transitions. For instance, transitions that do not have an activity or an intermediate event associated in the bpmn process model. And these transitions are called silent transitions because they are not represented in the process model, but they need to be represented in the process model. And we also see that not only intermediate events, as written here, but also start events and end events will also be represented as transition, the same as tasks, obviously, are also represented as transitions. Okay, so we have a number of mapping of translation rules. First of all, the execution of an activity is represented by firing of a transition. So if I have here one activity T, so a task, process task T, that is embedded in X and Y, always shows how to relate the resulting bpmn or Petri net fragment with the rest. So this is, let's say, the context of the task T. Task T is represented by a transition. If we look closely, then we see also a mismatch, a conceptual mismatch between the two. The one hand side, well, they are both incur activities, so an activity is executed, is enabled, starts running, at some point in time it is finished, it terminates. However, on the other hand, a transition just happens, so it has also an activity, it changes the state of a system, also that is the same as a task. However, it does not take time. So the firing of a transition is an atomic step, mentioning that before. It does not take time. So we have similar situation then with the trace semantic. Hope you remember that. We were discussing this earlier this week. So that the Petri net just has a transition, so merges somehow the begin and terminate state transition. It just has this state transition from ready to terminate it. So we just have these state transition. So a transition is enabled, and if a transition fires, it's terminated. So it goes from ready, from enabled, immediately to terminated. We need to map also events, and this slide shows you how to map events from BPMN to PetriNets. First of all, start events are represented by a fragment, a PetriNet fragment consisting of, so that's the left-hand side, you have the BPMN, just a start event S, continuation with Y. And here on the right-hand side, we have a place I, and that is the place I that is important, so the initial place. And the occurrence of the start event is represented by a transition S. So S is the transition. And once S fires, so once the process starts, then also there's a transition in the PetriNet. Transition S fires, so that the PetriNet also then reflects the starting of the process instance. In terms of intermediate events, we have here, we don't look at the internal structure of the intermediate events. We don't care about it. It's just important that something needs to happen there, and this something needs to happen is again represented by a transition and just the firing of a transition E. So if the previous activity is completed, then of course the intermediate event happens. It's also abstracted from the type of the intermediate event. So when I wait for a message and the message would not come, we cannot handle that on the formal level, right? So we assume that intermediate events will always occur because we can only analyze the behavior of a particular process model. We cannot analyze the complete environment. So we assume the environment behaves as specified, so that we can map this intermediate event just to one transition, E here. Regarding the final event in BPMN is represented by the output place O, so by the final place of the PetriNet. I also mentioned that PetriNets are very good at expressing split and join behavior, at least regarding AND and XOR. So the AND split, on the left-hand side here we have the AND split. And the AND split, is called A here, comes from X and has two concurrent branches, opening branches to Y1 and Y2. And that's represented by the normal split behavior of a transition. So when a transition fires, it puts a token on each of its outgoing places. And that's exactly what represents the AND split. And join is the same, so that it's also represented by a transition. However, at this point in time, the transition has input places from all the joins that need to be synchronized by the AND join. And only if all of the, in BPMN speech, all incoming sequence flows needs to be signaled. If all incoming sequence flows are signaled, the AND join fires. On the PetriNet, we have the same behavior. So if each input place of the transition A prime has a token, then the transition can fire. That's exactly what happens here. So A prime, transition A prime can only fire if I have a token here and here. In this case, a token is put then on the next follow-up place. Splitting behavior regarding the XOR split. So there's a decision D, and either the process continues with Y1 or with Y2. We can represent this behavior by two transitions. So we need two transitions, and we need two transitions called D1 and D2. So why is this exclusive OR behavior represented here? Now assume we have a token in X, and now D1 and D2 are enabled. But as soon as one fires, for instance, D1 fires, puts a token here, what it also does, it erases the token here so that D2 can no longer fire. So by this structure, exactly the XOR semantics, the exclusive split semantics is realized exactly by this. Again, there are no conditions attached because we are not looking into specific data as well. We just look at the set of possible behavior. The possible behavior, regardless of the conditions, is either I go for y1 or I go for y2. And this either I go for y1 or I go for y2 is represented by the PetriNet fragment on the right-hand side. The merging behavior of this XOR join is represented by this structure. So if I have, let's say, x1 is signaled and the bpmn level, so x1 is signaled, then that means x1 has a token here. And then d1 can fire, puts a token here, process continues. The same holds for x2. So if either one of the input of, let's say, this incoming sequence flow to the XOR join is triggered, then the XOR join, let's say, signals its outgoing edge, and the same behavior, we can achieve the same behavior of the PetriNet with this structure that either there's a token x1 or an x2. In both cases, or in the first case d1 prime fires, in the second case d2 prime fires. In any case, there's a token ny which allows the process to continue. Okay, now let's try to apply these transformations to our model. That would be a bit too much if I would try to start drawing this. So I took the shorthand, so to speak, and just put it here. But as an exercise, you will be invited to apply these rules. And you'll see that we'll come to the structure, to this PetriNet structure that represents the bpmn process model. So that's, of course, is the bpmn process model that we achieved earlier this week by making it structurally sound. So how is that done? First of all, we have the initial place here, and that reflects this newly created start event. We have the decision, and this XOR decision is represented by this structure. So either of these three transition fires, so only one of these three transitions, or this one, or that one, these are the also the silent transitions, therefore they are represented by this black structure, by this black little box. So either of these three silent transitions can fire, and then token is in P2, P3, or P4. And assume on the bpmn level the process receives the claim by surface mail, goes here, and then continues like that. Let's try to mimic that here. So what happens is that, first of all, I make some space by erasing this. So the process starts here in P1, goes here. That is the transition receive claim by surface mail occurs. So state transition from enable immediately to terminate to represent the conduction of this activity. Then we have this silent transition putting a token in P7. Then register claim can occur, putting a token here. Then decide on claim coverage can occur, putting a token here. So we see that the behavior, we could do that for also the other two, and we'll see that the behavior, that we have exactly the same behavior in the PetriNet as we have in the bpmn process model. That concludes video clip 3.6, in which we translated bpmn to PetriNets. We've seen how to translate activities, events, and gateways, and we illustrated that using an example.